Okay, now that you have listened to the lecture on conditional probability, the next logical step is to talk about the multiplication rule. Recall with conditional probability that we were looking for the probability of the second event in a sequence. Okay, so the question becomes, well, can we calculate the probability of the entire sequence, the first event and then the second event? And the answer is yes. That's where the multiplication rule comes in. So one of the things to keep in mind is that you will read the word and. All right, so this is going to be the probability of A and B, the probability of a sequence of events. All right, so in probability speak, this is the probability of A and B is going to be the probability of A times the probability of B given A has occurred. Okay, so again, rather than just the conditional probability, we're now multiplying it by the probability of the first event in the sequence. Okay, so if A and B are independent, how is this going to change? Well, think back to the last lecture. What is the conditional probability if A and B are independent? Right? Hopefully you are recalling that it's just the probability of the second event. All right, and so in which case, if A and B are independent, the probability of A and B is simply the probability of A times the probability of B. Okay? If we want to think about this in terms of a Venn diagram, all right, and here we've got A and B and they're overlapping. That gray shaded region that you see is the and space. Events in that gray area are in A and they are in B. So we want to try to calculate the probability of that intersection. All right, let's go through some classical examples. What is the probability of selecting a king and then selecting a queen? All right, so this is going to be the probability of a king and a queen. And using our formula, that's the probability of the first card, the king, times the probability of the second card, the queen, given we have a king in our hand. Okay, so how do we get that? Well, the probability of the king is pretty easy, right? That's just the number of kings in the deck divided by the total number of cards in the deck, times now the conditional probability, the number of queens in the deck given a king has been removed, divided by the number of cards given a king has been removed. All right, so what kind of fractions do we have here? How many kings are in the deck? All right, hopefully you're saying 4. All right, so we've got 4 over 52, the total number of cards in the deck, times the 4 queens, given you have a king in your hand, divided by 51, the number of cards given a king has been removed. And this equals about 0.6%. So pretty small likelihood. All right, let's consider the probability 2 hearts are selected without replacement. So in other words, this is I deal you a heart, you have it in your hand, and then I deal you another heart. What's that probability? All right, so the probability of a heart and a heart is going to equal the probability of the first heart times the probability of the second heart given you got a heart the first time. All right, so what are these fractions going to look like? All right, that first fraction, the probability of a heart, is simply the number of hearts divided by the total number of cards, times now the conditional probability. So now it's the number of hearts given a heart has been removed divided by the number of cards given a heart has been removed. All right, so for that first fraction, we have 13 hearts in the deck and 52 total cards. We remove a heart. So now there are 12 remaining hearts and 51 remaining cards. So we multiply these two fractions and get 5.9%. All right, the probability of tossing a head and then rolling a 6. Think back to the conditional probability lecture. How did we describe these events? Were they independent or dependent? So is flipping a coin and rolling a die independent events or dependent? And hopefully what you're thinking is they were independent. And so since they're independent, our formula is a little bit easier. This is simply going to be the probability of heads times the probability of rolling a 6. All right, and so how do we set up these fractions? We've got the number of heads divided by the total number of sides of a coin times the number of sixes divided by the number of sides of the die. So we're looking at 1/2 times 1 over 6, or 8.3%. Let's take a look at some empirical examples. All right, you're going to see these in the homework as well as on the quiz this week. So let's look at different ways to calculate empirical examples. The probability that a particular knee surgery is successful is 0.85, or 85%. Find the probability that 3 knee surgeries are successful. And the most important thing here before you start is to ask yourself, okay, are knee surgeries independent or dependent? And what I hope you're saying is they're independent. There's no way that one knee surgery has any bearing on the probability of another knee surgery's success or failure. All right, so since they are independent and we want the probability of 3, this is simply going to be the probability of successful times the probability of successful times the probability of successful, or 0.85 times itself 3 times. We can plug that in our calculator and get 61.4%. All right, what about this one? All right, same problem, but now we want to find the probability that none of the 3 knee surgeries are successful. All right, now recall from the introduction to probability, this is whenever we're dealing with none or no or not, this is dealing with the complement. So what we're going to do here is use the complement. This is the probability not successful times the probability not successful times the probability of not successful. Well, if the probability of success is 85%, what is the probability of not successful? And what you're hopefully thinking is, Angie, that's a really silly question. That's 15%. So what we're going to do is take 0.15 times itself 3 times, giving us 0.3% or 0.003. All right, so now let's take a look at the third way I can ask this question or deal with the question like this. And that is, now we want to find the probability that at least one of the knee surgeries is successful. Okay, so the probability of at least one. How might we calculate this? Well, the answer is it's going to use the complement of one of the previous problems. All right, so you guys like to have things you can memorize, all right, throw in your short-term memory. Anytime you read one of these problems and it says at least or at most, you're going to use the complement of one of your 2 previous answers. All right, we just got to think through what would the complement look like. All right, so here's the sample space for knee surgeries, all right, where S is successful and F is a failure. All right, let's look here, and it says find the probability that at least one of the knee surgeries is successful. So I have highlighted in red all of the ones that have at least one knee surgery successful. Notice everything is highlighted except FFF. Well, what is FFF? Well, FFF is that they all 3 fail, and none of the 3 knee surgeries are successful. Isn't that just this problem right here? Did we not calculate FFF? Yes, we did. This is not successful, not successful, not successful. So the probability of FFF is 0.003. So what's the probability of everything in red? All right, you guessed it, it's just going to be 1 minus the probability all 3 are not successful, or 1 minus 0.003. Final answer, 0.997. All right, let's do another empirical example. In a jury selection pool, 65% of the people are female. Of those 65%, 1 out of 4 works in a health field. Find the probability that a randomly selected person from the jury pool is female and works in a health field. All right, so this is the probability of the sequence of events, female and works in a health field. So this is, by our formula, going to be the probability of female times the probability of a health field worker, given that we got a female. All right, so we read 65% of the people are female, so we know the probability of female is 0.65. that second sentence in the problem says of those 65%. So in other words, of the females, 1 out of 4 works in a health field. So we have the conditional probability that the probability of a health field worker given female is 0.25 or 1 out of 4. Using those two statistics that are given to us in the problem, we can multiply them and get our probability of female and health field worker. So we take 0.65 times 0.25 and find that the probability is 16.25%. All right, how is it changing now? Now we want to find the probability that a randomly selected person from the jury pool is female and does not work in a health field. All right, so what's changing here? What's changing is that now we're interested in not health field worker. So that conditional probability is the probability of not health field worker given that we have a female. So again, we're seeing the word not, and hopefully your brain right now is firing the word complement. All right, so we're thinking complements coming into play. So we got the probability of female is 0.65, and then the probability of not a health field worker given female is 1 minus 0.25 or 0.75. So if we want the probability of female and not a health field worker, we take 0.65 times 0.75 and get 48.8%.